Lecture 26, Asynchronous I/O with select and poll. All right, we got onto this topic by finishing up our discussion of concurrency, and we were talking about how file systems do their magic, and it got us to the idea of, well, actually, sometimes when you do a write, all that really needs to happen is the write is acknowledged, and then it can proceed, and then after that, you continue going about your business, and the write in that case is what we would describe as asynchronous. We've transferred over all of the data that we needed to transfer, and yet we're able to continue, even though the data hasn't yet appeared on disk. So it turns out that we can get this kind of behavior as well, in general, and that is asynchronous I/O. That is, we can start something and we don't have to wait around for it to be finished. We'll find out, of course, that asynchronous I/O has its uses and its advantages and also its disadvantages. But it's a good tool to have in the toolbox when it comes to actually making sure that we can write a program in a way that makes sense for whatever problem we're trying to solve. If you've written something in, say, JavaScript, not the only language, but probably the most common one that looks like this, the whole idea of asynchronous is probably very familiar to you, because in JavaScript a lot of functions are asynchronous and you have to put in a callback that you invoke when the operation is finished, kind of thing, because that's just how the language works, and because it's single-threaded, it's the structure. So we'll talk about asynchronous quite a bit. You may think this is silly if you think about it in the context of purely a C program, because, well, you can always write a C program to have multiple threads, or at least usually you can. But what you learn about, say, asynchronous I/O can carry over to a different programming language where that's not a thing. All right, enough preamble. Let's get started. Okay. So, as we discussed a lot earlier, the standard read code, where you open a file and you open example.txt and you use the flags read-only, and then you call read on the file descriptor that you get back into a buffer, some number of bytes. That's blocking. So your program waits for the I/O operation to be complete before continuing on to the next statement. And this is sometimes, but not always, necessary or sensible. If you need the data in the next statement, then obviously you can't go on. You can't just proceed because you need the data to be there. So we read some data into the buffer, and now we're going to do something with that buffer. We need that. That's understandable, but other times, while we're waiting for something, if you're waiting for the bus, do you just stare off blankly into space, waiting for the bus to arrive, gaze wistfully into the middle distance like you are, the downtrodden protagonist of some romantic comedy? Probably not. Probably not. What do you do instead? You get out your phone, obviously. You pull out your phone, you use it for something. Whether you use it for productive purpose, like answer an email on a project that you're working on, or just liking posts on Facebook or whatever, is up to you. But you're doing something and you're making use of the time. And that's kind of the objective where we like to go with asynchronous I/O, which is that while we're waiting for something, if we have something to do in the meantime, maybe we should work on that thing, as opposed to just waiting and being blocked. You can see, I think, sort of the advantage to that. You can see why this would be valuable, is that, we can do work while we're waiting for the result, and then potentially finish, the total amount of work that we have to do in less time. Now, our main solution up until now has been threads, right? When you say, well, if a thread is going to get blocked on a read, well, we could just do that. We could create a new thread, and that thread can handle the I/O, and we'll carry on in a different thread. Totally normal. Perfectly fine. We're used to that. Maybe you don't want to use threads. Maybe you're worried about race conditions. Maybe you're concerned about the overhead of thread stacks. If you have enough threads, it does eventually get to be a bit of a problem. Maybe there's a limitation on the maximum number of threads that you can have. The last one actually might seem kind of ridiculous, but perhaps in an embedded system, you don't have the option to make new threads, or at least not as many threads as you've decided that you want. You might be limited in the number of threads that you are allowed to create. And as I mentioned somewhat in the introduction, sometimes your programming language, and JavaScript is one of them, is inherently single-threaded, and you just can't make more threads. So we have no choice. We have to do something along the lines of asynchronous I/O. Now, obviously, what asynchronous I/O tools you use will be different in different languages, but you'll get a good introduction to the concept and a good understanding of the idea in C in this course, and you can take that and you can apply it as needed to whatever project you want to work on. It's probably JavaScript. Okay, so listen, if we look through the flags for open, we'll find out that there exists the ability to add a non-block flag, and there we go. So we just call open example.txt with our usual read-only, okay, and we're going to tag on non-block, saying don't make this a blocking read, and well, we did it, right? No, sorry to say. No. If you open the file in non-blocking, the read call returns instantly whether or not the data is actually there, but it doesn't work for what we're doing. The non-block option seems, by its name, like it does what we need, but in practice does not. It says we should not wait for data when there's no data available. Assuming the file that we want to read data from exists, then data is available because the file is there and the file always has data available. It takes us a significant amount of time to get it because we have to wait for it to be loaded in from disk, which is not instant, but we can get it. It will eventually arrive. So, yeah, the non-block flag doesn't help us there. Is there some other scenario that you could think of where we don't always have data available? Yeah, if you said sockets, you are correct. This is an example of something that we already got into much earlier in the course of, well, here's some data. Maybe data is available, maybe it's arrived over the network, or maybe it hasn't. So with sockets, you can set your sockets to be non-blocking. If you haven't received data, and you just called read on a socket or receive or something like that, or accept or receive from, you would normally get blocked. But now we have the ability to say, actually, I don't want that behavior. We can change this by setting the socket, doing the following. So imagine that we are creating a socket. The actual arguments for creating the socket are not important, but we have a socket, and then we can use the file control function with the socket, and the command that we're going to give to this function is set flag. So we want to set properties about the file, i.e. the socket, and what we're going to do is use non-block, which says we want the non-blocking option to be set on that file, which represents that socket. And then we have a non-blocking socket, and that means that those operations that would normally cause us to get blocked would end up, well, not blocking whatever thread called that function. All right, so what does that look like in practice? Well, if you remember from, say, talking about try-lock as a concept, you will remember that what it really means is that when we do something like try-lock on a mutex, it's our responsibility to check whether we have succeeded. We have to take a look at the return value. And that's exactly what's going to happen here. If you call those and there is no data to receive, then they return a value of -1, and the error number variable will be set to either the E again, so error again, or E would block. Unfortunately, The specification does not say whether it would be again or would block, so you actually have to check for both to be fully correct and make your program work across platform. So yeah, that's a little bit of a pain, but fortunately it's just a small thing. It's not great, but it is how we're sure that we actually got a -1 as a result of there being no data available. Okay, so let's imagine then what a scenario would look like where we want to employ non-blocking sockets. I mean, I could jump right in to tell you about how to work with them. I mean, we have a basic idea now. We set the socket to be non-blocking, and then our calls don't block if there's no data available. But I think it would be a little easier to actually do it with an example where there is a scenario that you have in mind, and it would help you to visualize what we want to do and what we need and how we get there. So this is a common scenario, I think. We have a server application, and the server application is going to wait for incoming connections. And when incoming connections are established, then it communicates with those clients. Okay. You could have different threads listening on their individual sockets. That is a valid option. So like when a connection is incoming, you create a new thread corresponding to the handler function that handles that connection. So you give the new socket to that thread, and you communicate over that newly created socket from the new thread. That's okay. That's allowed. But give us the scenario again that we can't create more threads, or we don't want to for some reason. We will work off the basis that we have to do it without threads, or alternatively, if you want to view it more positively, we no longer have to use threads for this option. So the problem, of course, that we have so far is that on a server application, if we're listening on several sockets, so there are 3 clients who are connected with us right now, we can't very easily accomplish our goal without wasting a lot of time. If we just poll each socket using accept, and if we get back -1, we see, oh, data's not ready, then we just go on to the next one and then try again. We're doing what is effectively tight polling. That is, we're checking repeatedly. Admittedly, we're alternating between 3 sockets, but still, we're not exactly accomplishing a lot, and we're wasting a lot of CPU time while we wait for one of them to have some data. On the other hand, we can't just do regular accept with blocking threads, because if we call accept or receive on socket 1 and some incoming data appears on socket 3, we can not get there because we're blocked on socket 1. So that's not going to work for us either. So if we don't like the idea of tight polling, CPU-intensive time wasting, but we don't want to get blocked on a particular socket because it's not necessarily where the next set of data is coming from, what do? We need a third option. We need something else that works for us. Select. Yeah, I'm looking for Sarah Connor. This is... what are we selecting here? Okay. The third option is actually called select. And select is used to monitor a group of sockets or a set of sockets, depending on how you want to think about it. And a socket could be ready for reading, ready for a write. Obviously, you can't write an infinite amount of data into a socket, but at least write some chunk. Or whether an exception of some sort has occurred. Now, when I say exception, I don't mean in the Java language or the C++ language or the C# language version of exceptions. I mean that there is some unusual state, some special case information that isn't normally sending or receiving of data. We're not actually going to focus too much on exceptions. We'll think about just sort of reading and writing. But in theory, the select function can work with all kinds of things that you want to watch for. There are accordingly 3 sets of sockets that are provided. So, select, when it comes down to it, select is a function I really don't much like because it asks a lot of you as the caller. It requires you as the person who's writing the code that's going to invoke select to really cut up the food for select and make its life, I'll say, easier. So the function signature for select takes a lot of arguments. NFDS is our first argument. It is supposed to be the value of the highest number file descriptor in any of the three sets plus 1. This is what I mean about select requiring you to cut up its food for it. If we call select, we get blocked until something happens on one of the sockets in the three sets, and then there is also a timeout parameter, and the timeout parameter is allows you to set a maximum time that you're willing to wait for something to happen. Okay. While blocked, you could also get interrupted by a signal or something to that effect, so that would also wake you up, even if no data has arrived. But usually it would be you are waiting for something to happen on one of these sockets, or you reach the timeout, and you've decided you're not going to wait anymore. Okay, so NFDS is the value of the highest number file descriptor. So in your socket sets, you put in the sockets that you want to watch. So if things that you want to read from, sockets that you want to read from, you put in the read FDS set, and you have to keep track of what socket has the highest number amongst any of these, and then use that plus 1 as NFDS. What's this about? So, like I say, it has come to this. One of the problems with select is that it's kind of arcane. The documentation says that you have to provide NFDS because select scans through all the file descriptors from 0 up to this number, so up to NFDS minus 1, to figure out if we care about them. Why is that? Well, the FD-set structure can have a maximum of 1024 file descriptors, and it's implemented as a bit field. The specified highest file descriptor tells the kernel it can stop iterating over this array, or this bit array, once you reach the last one, once you reach the highest number, and that means the FD-set structure doesn't have to be implemented as a linked list or anything large. Not a fan, but that's how it works. I'm just the messenger. Don't be mad at me at how terrible select is to ask this of you. Now, the FD-set parameter represents a set of file descriptors, as you might imagine, and like a number of the structures that we've talked about, we don't actually care all that much about its internals. I've told you that it's implemented here as this bit field and contain a maximum of 1024, and it gives you probably a decent idea of how the FD set is implemented, but the only reason I explain that to you is so you know why this NFDS thing is required. Absent that, the actual physical implementation of what is an FD set is kind of irrelevant to us, in the same way that we don't care what a pthread T structure is like. Its internals are irrelevant to us, and we don't rely on any particular implementation data about how it works internally. Same thing with the FD set. So it represents a set of file descriptors. Not surprising at all. And we are provided a bunch of functions which are used to manipulate an FD set. So when you create an FD set structure, it is basically a requirement to initialize it with FD0, and again, just takes a pointer to this set that you want to initialize. And it's also used to clear the set, so if you wanted to get everything out of it and start anew, you would use the FD0 function for that as well. And then there are set, clear, and isSet functions, which are used in conjunction with a set and a file descriptor. So if you want to add a socket to an FD set, you just use the FD set function, specifying this is the file descriptor I want to add to this set. And to remove it, fd clear, so again, remove the following file descriptor from the given set. And then int fd is set turns out to return whether or not fd is part of the set. Yes, it returns an integer, but in this case, int is used as a Boolean. C doesn't really have a Boolean, if you remember, so that's how it ended up being the way that it is. It returns an int instead. Okay, now fd is set. I mean, it's not likely, I think, that we're going to forget whether we put a socket in there. The real purpose of fd is set is for looking at what select returns. We can find out whether a file descriptor is in a set by checking against the returned value with the fd is set function. Okay, so there are three sets of file descriptors that are provided. The read FDs, so those are sockets that we want to read from, so we want to wait until data is available to read on those. Write FDs is sockets we're interested in writing to. It says writing from, but it should say writing to on the slide. And yeah, except FDS, like I said before, this isn't Java, so it's not, socket does not feel like doing work right now exception. No. Exceptions are, more things like, is there out-of-band data on a TCP socket or anything like that? We didn't cover that earlier when we talked about network communication, and truthfully, we're not going to cover it now. But you should be able to find out if a socket is in that state if you have a reason. Like I said, we're not going to cover that, and we're not going to do any examples involving sockets in the exceptional state, but at least I give you the complete picture so you know what that's about. Okay. So we don't have to use all three of read, write, and accept file descriptors in a call to select if you don't need them all. You can provide null for anything that you don't care about. So if you don't care about sockets that are in an exceptional state, you just provide null for that argument in the call to select. And I mentioned earlier that there is a timeout, and timeout is specified using a struct timeval. And timeval is made up of two long types, so long integers, seconds and microseconds. Okay, so yeah, the granularity that you work with it seems a little strange. Why do you specify in seconds and microseconds? But that's just how it is in the spec, and the structure at least is fairly straightforward. If you provide a struct timeval where both fields are 0, select returns immediately. So if there was data available on the sockets, it will tell you that. If not, it says, nope, nothing is ready right now, and you've reached the timeout instantly. Otherwise, it waits for up to the specified amount of time. If something happens, we're waiting for a socket to be ready for reading, and that happens before the timeout is reached, then we wake up when the data is ready, i.e. we don't wait for the timeout. And if you give in null for the last argument, the pointer that should point to the timeval structure, then select will wait indefinitely. It will wait until some data has arrived, however long that takes. Could be a very long time. Okay. And here's the number one reason why I do not like select, and it's just, this is against my preferences. You can make an argument that actually select is great. It's just my opinion. That's just like your opinion, man. But the thing is that change is painful. When select returns, whether it was we reached the timeout, whether it was some data has occurred, whether or not an interrupt happened, something like that, some, if not all of the parameters got updated other than NFDS. So we passed in a set of file descriptors for read, a set for write, a set for exception, and those all got modified by select. They're modified in place to see if they change status, and the struct timeval is even worse because the FD sets are modified, they're overwritten, you know that they are different, but the time val may but may not be updated to reflect how much time is left before the timeout when we got woken up. So on some systems, the time val does not change, so it isn't updated at all. On others, it is updated to reflect how much time was left. So if we said we're going to wait for 5 seconds and something happened after half a second, then it will be updated to say, oh, it's at 4.5 seconds. If you got to the timeout, it will tell you that the remaining time is 0, but not always. Because different systems may or may not change the time val, it's not safe to reuse the time val struct after you have called select. You have to reinitialize it, overwrite it if you plan to use the time val again. And yeah, unfortunately, so after select has returned, we have to check the file descriptors in our sets. So if you put 10 sockets into the read set, you have to check every single one. So with a loop or something, or individually, you check them all to determine, okay, did anything happen on socket 1? Did anything happen on socket 2? How about socket 3? Socket 4? This is the way that select works. It returns when there is something to do, but it doesn't tell you what socket or sockets, plural, are ready. So we have to check each socket to see if it's ready, and we do that using the fd isSet function. So you say, is socket 1 in the new version of the read fd set? If so, then yes, that socket is ready for reading. And you have to do that with every single one. Okay, so we have a lot of work to do, as I say, to prepare everything. We got to put all our sockets in the FD set. We give them into select. Select changes the FD set, and then we have to iterate over all of the sockets that we were watching before to see if it's now still in the set returned. And if it is, that means that something happened on that socket and it's ready to go. So it is likely, in particular in any kind of server application where you want to wait for incoming connections and wait for incoming requests, that you're going to do this in a loop. That you will wait when there's a request, you will take it, you will deal with it, you will handle it. Because you're going to do this in a loop, every time you need to call select, you have to go over everything again. You have to rebuild all your sets of file descriptors, maybe with some modifications. If you are removing sockets from the list that you care about once an event has occurred, then you can just drop it and you don't put it in the rebuilt set. But however you do it, you can't just take the output from select and use it again. We have to rebuild all of our sets and send those into select refreshed. So yeah, select really does ask quite a lot of you. And we're going to now sort of imagine a brief example. We have a server that's going to listen on 3 different sockets for 3 different services. They are imaginatively called Service 1, Service 2, and Service 3. Okay, so I've written a function here, listen for connections, and it takes 3 sockets, the ones that are relevant for Service 1, Service 2, and Service 3. And NFDS is then calculated here in the first line of the function. As I recall in the past, there were a couple of questions about the formatting of this line. This uses the ternary operator. It's called the ternary operator because it actually takes 3 arguments. A unary operator is like negation, while not quit, that's a unary operator because it only takes 1 operand. A binary operator takes 2, so mathematical addition or logical OR. And this is the ternary operator in C, and it appears in other C-like languages as well. In that, it's like an if-then-else kind of behavior. So if service 1 socket has an integer is larger than service 2 socket, then we do the branch that follows the question mark, and then if not, the else is the colon. So, based on this, if service 1 socket is bigger than service 2 socket, we go and we compute this branch, which itself has a ternary operator in it. And so service 1 socket is greater than 3. If that's the case, it's the biggest. And so that is the winner. Otherwise, service 3 socket is bigger than 1, which is bigger than 2. So service 3 socket is the highest number. And of course, we get the reverse down here. If service 2 is bigger, compare it against 3. It's just a sort of syntactically neat way of computing this NFDS. This would be a huge pain if we had more than 3 sockets, so you would probably, use a for loop or something where you just remember the maximum value if you had a lot of sockets to do this on, but for now, this will suffice. So we're going to declare an FD set called S, and we're going to also set up a struct timeval TV. And then there's a little printf here that says we're going to start listening for socket events. Now, we're only going to use one kind of socket here. We're only going to read on them. That's fine. The purpose of this is to demonstrate how to work with select. It's not necessarily extensive exercising of all options. Okay, and then we have our loop. And in the loop, on every iteration, we have to reinitialize our file descriptor set S, and we will add sockets 1, 2, and 3 to that set, and we will set up our timeout to be 30 seconds. All right. Once we've done that, we can then actually call select. And select will return an integer value, as we know, so we're going to capture that as a variable res here. In NFDS, we calculated with our ternary operator, and we're only interested in reading from each of these, so we will provide S, our FD set, for read FDs, and null for the other two kinds, write and exception, because we don't care. And a pointer to our timeval structure, which is used to set the timeout. So if the return value of select is -1, an error occurred in select for some reason, and we're just going to print the error as returned from error number, and we'll just quit. We'll break out of the loop. It's good to have the error handling, so we did not overlook it here. If result is 0, it means that 0 sockets event occurred while we were waiting. And that's actually what the return value is. If it is a positive number, it will say, oh, there are 10 events that occurred while we were waiting, or 10 of them were ready at the time that we called select, which is also possible. In which case, then the result would be a positive number. It would say, oh, it's 10. We don't usually look at that. All we care about is it -1, is it 0? Anything else, we will proceed into handling. So I wrote in here that if result is 0, it means that no events have occurred recently, but I've set up a little printout here to the console, printf saying still waiting, nothing has occurred recently, which just, if you were taking this code and running it, would give you reassurance that the system isn't frozen, nothing is stuck, nothing bad has happened. I wrote this kind of thing for example, for the Rogue One server exercise, something you'll be familiar with as well, that for sort of my own purposes, I put in a printf saying, still waiting, just to make sure we're still alive. Makes it sort of easy to check on the server when I'm testing it out, that didn't get stuck. Okay, but assuming that something actually happened, then we'll take a look and see. So we have to check each of the file descriptors to see, well, if socket 1 is the one that activated, then take some action. Service 1, activate. Thundercats or go. Yeah, I didn't write an implementation for each of the activate functions, but yeah, if what we were waiting for happened, then we can do something with it, and we can go on to that function. And you'll notice that we have to check every single one, because more than one of them could become ready at once. The activate calls could take some non-trivial time, so if a socket receives some data in the meantime, Then potentially on the next iteration of the loop, select will return immediately because data is already waiting. And if that's the case, then select doesn't delay you at all. It just tells you, yep, some of them are ready, so let's go. What if connections, however, are supposed to stay open for some longer period of time, right? In this fairly simple scenario, we're just waiting for accept on the services, where maybe we send back a simple response, and that's the end of it. If there is like occasional communication, then we might have to manage this a little bit better. And what do I mean by occasional communication? Well, I'm thinking of, like, imagine there is a chat server kind of thing. So thing is that, like, with chat rooms, people can come and go. We have to add and remove sockets from the sets as connections are opened and closed, and managing the sets is non-trivial, of course, because select changes everything out from under you, so you can really suffer with the way that select does things. So here's the scenario that we want to examine. It is a chat server. If you ever used IRC, Internet Relay Chat, you have a pretty good idea of how this would work. If IRC is foreign to you, the best descriptor I ever heard about IRC is that it is multiplayer notepad. It is just a basic, text chat communication program. There's no pictures, there's no animated anything. It's all just, you write some text and other people see the text and so on. The IRC protocol is somewhat easy to implement, so you could write your own implementation of it if you wished, but that would be just sort of an interesting, fun project. And some IRC channels are still used widely these days. They're not as common as they used to be. I think especially because Discord and other such services have kind of taken that market. But nevertheless, the idea of multiplayer notepad, I hope, is a good concept with which to start. So, okay, what happens when people are in a chat room of some sort, and it feels incredibly 90s to say the chat room, surfing the net, going on those chat rooms. Okay, so when you want to join one of these rooms, you send a message to a server saying, like, hey, I would like to join this room. Okay, that part's still valid for any such thing, even Zoom sessions or WebEx or what have you that we do now. You indicate you want to join a given server, and that's what you do. So the server accepts, opens the connection, and then adds a client to the chat room, but it is not always the case that people are constantly talking. In fact, lots of people do much more listening than they do typing, or reading than they do typing. So that's actually fine. If everybody was talking all the time, it would be quite hard to follow along, but it's more likely that, some people are writing, other people are reading, so not everyone is writing at the same time. So if nothing is happening right now, there's nothing to send. When there is something to send, we get a message from somebody, and then the server is going to send that message out to everybody else. This person joined, and they said hello. We send that hello message out to all of the other clients who are in that room. Either way, if you're the server, you are waiting for something to happen. You're either waiting for the socket for incoming connections, so when a new client wants to join the chat room, you wait on that one, but also you're waiting to see if anybody said something. And that would be a socket that we have with an existing client. So when we wake up from our select, we activate and we take the action that we are supposed to take. If it was the socket for new incoming connections, then you activate and you add the new socket to the list that we are going to listen to. It's the set that we are monitoring. And a chat server could then at that point send a notification to all the other clients to let them know a new person has joined the room. You will notice that usually happens. You will get some small notification that says Bob joined this room, and that is it makes it a little less surprising if Bob says something, right? And then to do that, of course, you just write a little information to the sockets that represent the connected clients. You just specify, yep, this is the message. You create the message, you send it off. Now, if it was not the socket for incoming connections that activated, it means that somebody said something, usually. So you read from the socket that's ready, you just read that message, and then you redistribute it by sending it out to all the other clients by writing and saying, after Bob joined, it sent out a message that said, hello, and now Alice is writing back and saying, oh, good to see you, Bob. So that would be, the socket for Alice is activated, and then it's going to be a message from Alice. We're going to pick that up, and we're going to send that out to everybody. Thing is, though, sometimes when a socket is activated, there actually wasn't a message to say. A socket will show up as being ready for reading if it has closed, and the call to read will return 0, so like 0 bytes read or a negative number, an error of some sort, if the socket has closed because a client has disconnected. And if the connection has been closed, then you remove the socket from the list or the array or the set that you're interested in. And we also sometimes send a message to other clients saying, this person left the chat, Donna has left the chat. Again, makes it a little less surprising. But if somebody really did say something, we just collect it, and the server will send it on to the other clients. The clients are waiting to receive messages, and they show them to the user when someone says something. So a client does a read on its side of messages that were sent by the server, and the client will see, here's an incoming message. It's from Alice. It says, good to see you, Bob. And then it will display that so the user can read it. And look at that. You are talking to strangers on the internet. Just don't give out your personal information. 1990s advice, don't talk to strangers, never accept a ride from a stranger, and don't meet up with people on the internet. Yeah, in 2020, use your phone to meet up with people from the internet and get in their car to drive you, because that's called Uber. Yeah, why not? Just be careful about how you give out your personal information. But yeah, we have the basic outline now of how to write a chat server. I mean, this is not exactly a fully featured system, and we haven't covered any of the things that you would really need. Security is a consideration. Can you kick people out of the chat room? Can you ban people who behave badly? You would need all those kinds of things. Can you stop people from spamming? And can you keep them from impersonating other people? That kind of thing is also sort of an open question as to how you would want to implement that on your chat server. There might also be some consideration given to periodic connection keep alive messages, so that you don't lose connections with people even if nobody's talking right now. So you might have to send out little messages that just keep the connection open so it doesn't get stale. The goal of this explanation was really not to tell you about how to write a chat server in great detail. It's not a design discussion of how to build one. The goal was just to give you an example of how you could use pselect to do something useful. All right, maybe you debate whether or not writing a chat server is useful or if that's just like a waste of time, but it is a practical application of using pselect. Closely related to pselect is the pselect function. So what's pselect? Well, it's very similar to select, but it has a couple of interesting differences. You still have to do the NFDS stuff. You still have to create your FD sets for read, write, and exceptions. But the last two things are a little different. There is a time spec instead of a time val, and there is a sig mask. So the time spec is kind of like a time val, but pselect promises it will never change it, so you can provide it, and the function won't change its value, so you don't have to reset it on the next invocation. However, it's slightly different in that it's seconds and nanoseconds instead of seconds and actually, I should say microseconds. So, yep, that's that again slightly different for reasons that are unclear. I guess you can be more precise with a time spec, but there's also a signal mask. Okay, you will remember, I think, from the much earlier discussion about signals in general, the idea of signal masks and that they're used to block specific signals. That if you are not interested in receiving a signal right now and you'd like for it to be deferred, that's what a signal mask is for. So yeah, we can do that. The thing that's really cool about this is it allows us to change the signal mask atomically in the same step as the call to select. Well, in this case, pselect. And you can choose what signals are allowed to wake up this thread while we're waiting for something to happen. And so you give in the signal mask, and, well, looks something like this. So pselect is called, assuming everything is initialized and worked with appropriately, where you specify the maximum file descriptor +1 in NFDS, your sets of read, write, and accept files could be null, your timeout, this time as a time spec, instead, and then your signal mask. And that's equivalent to an atomic operation doing all of the following. So we have an original sig mask. Okay, the atomic step doesn't cover the allocation of the sig mask, but the 3 steps following, where you set the signal mask, and then you do select, and then you restore the original signal mask. You may notice, actually, that the function here, pthread sigmask, looks different than what we did when we worked with signal masks before. In the past, we were setting it at a process level, where we used our system called sigproc mask. Now we are setting it for a thread individually. It's not really any different. The function signature is effectively the same, but now we're saying just for this thread only, we are interested in setting the following signals. If your process has only one thread, then setting it for this thread only is equivalent to setting it for the whole process. So yeah, things are not super different. It's just a slight variation on something we saw already, so hopefully at this point we can take it in stride, even if we don't have any direct experience with that function. Now, the advantage to using pselect to do this is, of course, well, if we wanted to do the operations below where there's 3 separate function calls, there's always the possibility that something weird goes on between changing the signal mask and the call to select. Whereas we would like to perhaps do it atomically, or at the very least just with less typing, which has its own virtue. Maybe I say that because I spent a bunch of time today working on a thing that's not especially hard, but just requires a lot of boilerplate to be written, and that's just how things are sometimes in programming. So anything you could do that could reduce the typing would be good. I only wanted a nap. Okay, so it's possible to misuse a call to either select or pselect as a way to make a very portable call to put the current thread to sleep. Some of the calls to sleep functions don't work super well on other Unix and Unix-like systems, especially if you want a very short sleep. Something on the order of seconds or is probably going to be fine. Seconds or minutes, you can definitely sleep for that long. But something on the order of microseconds or nanoseconds is not super portable. But select is in the standard. So what you actually do is you call select with all 3 file descriptor sets empty, NFDS is 0, and then you use the time val or the time spec to make the sleep timeout whatever you wish. So yeah, that's one way to do it, to put the current thread to sleep. Clever. Sometimes clever is bad, but in this case, I don't think I could even be mad. I think it's kind of clever. Okay, the next alternative that we're going to talk about is called poll. And poll is intended to like address some of the things about select that make it hard to do. So it's very much like select. It's you could call them cousins, I guess. And like its cousin, it's used to watch file descriptors to see if any of them are ready for an I/O operation. But poll asks less of you as the caller as compared to select. So the signature for this is, again, it returns an int, as is common, and then an array of struct pollFD, and then the number of items in that array, and then a timeout, and the timeout is measured in milliseconds. So, I mean, you can see immediately how much less this asks of you. You don't have to put things into file descriptor sets. You don't have to break them up based on the kind of thing that you're looking for. You don't have to calculate the maximum number or anything like that. We provide an array that says these are the poll descriptors that we're interested in, and then we also have to provide the length of the array because this is C. And that is most of what we need. All right, so let's get started. So we'll show you in just a moment the structure of the struct pollFD. It's how you describe this is the socket that I want to monitor and for what. And for what means for what events in this case. The length of the array, again, straightforward. And the last one, timeout in milliseconds. If you specify 0, it means don't wait at all, and negative number means wait indefinitely. Okay, so what is in a pollFD structure? Well, it's also fairly simple. It doesn't require any manipulation using some strange function. We can see exactly what's in it, so it's not exactly full of surprises here, is it? You specify this is the file descriptor that I want to watch, and then a set of events. It's actually a short. These are the requested events. And then there is our events. It's the returned events. Okay, so events is filled in by you, the caller, to specify these are the things that I want to watch for. And our events is updated by the kernel to tell you about what event or events have actually occurred. So that actually is quite nice compared to already what we've just covered with select. With select, the events things would be changed. The file descriptor sets are changed. But poll is not like that. The pollFD structure, the kernel changes our events, but when you're passing it in, all it cares about are the events. So those are not overwritten. They remain the same. That's good. So what can you watch for? You can watch for a socket that's ready to read with the constant poll in. You just put that in the events. You can combine events with bitwise OR operator if you want, but for event type read, that's poll in. A socket where you can write without getting blocked, you're looking for event type poll out. An exception, again in the concept we've talked about as they relate to socket, is watch for with poll pry. I'm not sure off the cuff why pry, but that's what it's called. And you can combine, as I say, the bitwise OR operator if you want more than one. And the return value is also constructed as a bitwise OR of the field, so you have to sort of unpack the result a little bit using the bitwise AND operator. But that is relatively straightforward. We'll see when we actually go to an example about how to do that. And return values can also include a few other things other than a read. So if we're ready to read on a socket, the returned events includes poll in, but we could also see poll error, poll hang up, or poll nval. So what do those mean? Poll error means obviously an error has occurred. Poll hang up, HUP, is used to indicate if the other side ended the connection. So if they closed their socket they were communicating with, then that is sent over to us as a hang up event. And poll nval is actually for invalid, and it's what happens if there's a problem with the socket, like it's not initialized. For example, you try to add a socket that isn't initialized to the poll set to watch, and it will tell you no, it can't. by having the return type be nval. Okay, now as before, when we wake up from poll, we know that something happened, but we don't know exactly what. So we will have to do a little bit of work to make a determination about what has happened, but it is, as I say, less painful than the select version. So now we're going to rewrite the 3-service example that we did previously in select to see its poll equivalent. If that had happened in a previous lecture, I would probably go back and review it, but hopefully it's still fresh in your memory at the time when you watch this. Otherwise, you could just scroll back a bit in the video feed to get to where we looked at it. But we have 3 sockets, service 1, service 2, and service 3 socket, and we're going to use all of them. We're just interested in reading from them. So we will declare an array of struct pollFD, and I'm just going to call it pollFDS, and it will be of size 3. And we will initialize the FD and the events fields for each of those structures. So pollFD 0 is assigned service 1 socket, and we're interested in poll in on each of them. And then we're going to set a timeout. Timeout is measured in milliseconds, and just for the sake of clarity, I did the 30 times 1,000 here to represent our timeout is 30 seconds. I could have obviously just written it as 30,000. But frequently, when I write this kind of thing in source code, when you write a timeout or something, I just do the multiplication because it makes it a little bit clearer for the reader why that's happening. And don't be concerned, the compiler will do the multiplication, so it will not slow down your program even one cycle at runtime to have to calculate what is 30 times 1,000. In any case, once we've done all our setup, then we're going to start listening for socket events. And you'll notice already that our setup is somewhat straightforward, at least as compared to select, because we didn't have to figure out which of the sockets has the highest number and calculate NFDS. And also, our setup of the pollFD's structure array happens once. It happens outside the loop. We don't have to do it on every iteration of the loop, as we did with select, because select would change these things, but poll will not. So this array can be set up just the first time before we enter the loop. Okay, and then we have the loop. The loop is, of course, smaller because, again, there isn't all that resetting of everything that has to happen at the beginning. And calling poll is straightforward. Call poll, it returns a result. We are giving an address of our array. The size in this case is fixed at 3 because I declared it to be exactly 3, and then the timeout structure that we've declared, timeout value that we've declared as well. And if result is -1, as before, if something goes wrong, then we get back -1, and the error number variable is set. So we have to remember to check that and take a look at it. If result is 0, nothing had an event occur, so still waiting, nothing occurred recently is printed again. And then if something has happened, we're going to wake up, and we do still have to check each of the sockets to see if they were the one that activated, but this is not so bad. We just check pollFD is 0, and if we check the R events value, we check it using the bitwise AND operator. So it could be that you get multiple things returned in R events, but you can sort out each individual one by using the R events in conjunction with this bitwise AND. So if poll in has occurred, great. We have the indication that this has happened on socket that corresponds to service 1, so we activate service 1. Same thing for 2, same thing for 3, and then we are all done, and we go around the next iteration of the loop. So yeah, which is which? Which is better? Well, I think it's obvious that my personal preference runs toward poll, but there's nothing I think, surprising about that. Both functions do the same job. It's really just what does the API call look like. That's what makes the difference between the two of them. You might have experience with one or the other, or you might have a preference for one or the other, and I would say neither of those is wrong. Poll doesn't ask you quite so much as the caller. You don't have to manage 3 different sets. You don't have to rebuild the sets on each iteration of the loop. You don't have to calculate what is the maximum file descriptor, and you could forget to put the +1. So yeah, it's got its disadvantages. But select and poll do have this drawback that they are slow in that they have linear characteristics. The more file descriptors you give them, the slower they get. And if you get up to about 100 different file descriptors, you end up spending a significant amount of CPU time trying to figure out which of the sockets have changed, and you can see how that gets to be the case. Right, if we're watching 100 sockets, we have a for loop, and so we iterate over it. Was it socket this? No. Was it this one? No. Was it that other one? No. Get down the list. Maybe 50 sockets later, you finally find one that did activate, and you take some action, and then you keep looking through the rest of the sockets, just to make sure that maybe socket 87 activated. That ends up taking up a significant amount of time. We might not actually like that if we're managing a large number of sockets. If the number is small, it's not a concern, and we can handle it. So if you want to do things more efficiently, we're going to have to use a different tool. And different tool for that is specifically libevent. And libevent is going to be sort of the last thing that we cover as a regular lecture topic. But I want to take a slight digression before we get there, because if you remember when we talked about sockets earlier, we were talking about them in interprocess communication and network communication. We followed that up immediately with curl. And we know, or we may have seen, or we're about to find out, that curl has a non-blocking option as well. So that's what we're going to do next. We'll learn about how to use the non-blocking interface for curl. So see you in the next video.